Good morning and welcome. I got into a conversation recently about the Flat Earth movement, and I said I was planning a video explaining how you could know the Earth is round. The person I was talking to basically told me that I was wasting my time because there's so much conflicting information out there that it's impossible for the average person to know what's true. His point was that if people on both sides were simply making claims and sounded credible, that there was no way to distinguish between them. I could understand where he was coming from, but I wasn't convinced. I think that, at least on the matter of the shape of the Earth, it's pretty easy to see who has it right if you just know enough to be able to test it for yourself. Therefore, unlike my previous video on this topic, in this video I intend to show how you, gentle viewer, can make some simple observations that should be enough to convince you that the Earth is indeed a globe. You won't have to take my word for anything. You'll be able to check the facts out for yourself. The hypothesis we want to test is that the Earth is roughly spherical, and that it's rotating about a fixed axis, and that all the heavenly bodies, except maybe the moon, are extremely far away. Contrast this to the flat Earth, which says that the Earth is flat, usually a disc shape, and that the sun, moon, stars, planets are all above the Earth and move around above the Earth. So, in order to test this out, I'm going to basically give you a little planetarium show, and I'm using a program called Stellarium, which you can download for yourself. I'll put a link in the description. And I encourage you to download it yourself and try this out for yourself. Stellarium will tell you, or will show you, what the sky, according to the globe Earth model, it'll show you what the sky should look like at any time and place. So here I've got Stellarium set up to show us what the sky looks like from the North Pole of the Earth in December 2019. Here we have a nice dark sky, and we're looking to the south, although there's no other direction to look when you're at the North Pole. And here we can see the stars, and it's kind of an unremarkable nighttime sky. Now, what we could notice is that if we scroll up so that we're looking directly upward, there's the North Star Polaris. And if I speed up the time in the simulation, you can see the stars rotate around Polaris. So this shouldn't come as a surprise to anyone. Whether you're in the globe Earth or the flat Earth hypothesis, we should see this. Whereas the North Star, which is right near what we call the North Celestial Pole, which is the point all these stars rotate around, is directly overhead when we're standing at the North Pole. Now, I'm going to turn on an equatorial grid. Okay, and this is like latitude and longitude for the sky. It's actually called right ascension and declination, but it's basically the same idea as latitude and longitude. So this point in the center where all the lines come together is the North Celestial Pole. And you can see Polaris is very close to it. It's about 1 degree away from it. Now, if we go back down to the horizon, you can see that the stars are rotating around the North Celestial Pole, and they're going parallel to the horizon. So they're moving horizontally. They're just going to the side. And everything is moving around in circles around the pole. So what I want to take a look at is what the sky looks like at different places on the Earth. You know, the flat Earth may work well enough if you're at the North Pole, but as far as I know, none of my viewers actually live at the North Pole. So let's take a look. I will open up the location window and move us to New York City. Okay, now, here the sun has just come up. I'll speed up time so that the sun goes back down again and then slow it down again. Now, here, we're at New York City, which has a north latitude of just under 41 degrees. Polaris is no longer directly overhead. Instead, Polaris is 41 degrees above the horizon, which is not a coincidence that the distance between Polaris and the horizon is the same as our latitude. You'll find that at the North Pole, which has a 90-degree north latitude, Polaris is 90 degrees above the horizon. Here in New York, the North Celestial Pole is just 41 degrees above the horizon. And if we look to the... Now, we will also notice that the stars, and I'll speed them up a little more, are making circles around Polaris. Still. And if we go to the side, we see there are bigger and bigger circles until we get to the east, where we can see that the stars in the east are rising at an angle. And it should also come as no surprise that this is an angle of 41 degrees from the vertical. And basically what we'll see as we travel to different places is the angle between the horizon and the North Star is going to be equal to our latitude, and the angle that things rise at in the east is going to be off from the vertical by an angle equal to our latitude. If we go further south than east, we can see that there are circles. The stars are still moving in circles, but maybe the circles aren't any larger. They're actually maybe getting a little smaller. The radius of the circles is getting a little smaller. So if we go now further south, so let's turn to the north. I will go further south. Let's go to Miami Beach. Now, Miami Beach has a, whoops, didn't mean to click that. Miami Beach has a latitude of just under 26 degrees. So now the North Celestial Pole is 26 degrees above the horizon. The stars, the sun, the moon, and the planets rise in the east at 26 degrees away from vertical. And if we look toward the south, the circles that the stars follow are getting smaller, and the lines of right ascension, which are like longitude for the sky, are starting to converge. Now, this is not something that the flat Earth predicts. The flat Earth predicts that everything rotates around the north celestial pole, and that as you get further from the north celestial pole, everything should follow bigger and bigger circles. Well, let's take a look at what happens when we're actually at the equator. So we're going to go to the country of Ecuador. Now, here's a city called Nueva Loja in Ecuador. Now you can see here in Ecuador, looking north, the north celestial pole is right on the horizon. And if we look to the east, we're at the sun, the moon, the stars rise directly vertically. And in the west, they set directly vertically. So there's the sun setting straight down. All right. This is because we're at 0 latitude. And so the angle with the vertical is 0 degrees. Directly vertical. So if you're in a country that's near the equator, the sun will rise directly vertically. And you'll find that in those places, the sunrise and sunset are very abrupt because the sun is not going at a grazing angle to the horizon. It goes straight up. So it doesn't take long for it to get bright in the morning or for it to get dark in the evening. Now, the interesting thing here is if you look south, wait a minute, what's going on? The lines are actually converging to a point, and everything in the south is rotating around another pole. This is called the south celestial pole. Now, if we wait for the sun to go down here, whoops. I didn't mean to speed up time that much. We wait for the sun to go down. Here we can see the stars are rotating around another pole. So what's happening here? Well, in the globe Earth model, this makes perfect sense because the globe is symmetrical and has 2 poles. But in the flat Earth model, this doesn't make sense because in the flat Earth model, there's only 1 pole. And basically everything should rotate around it. And as you get further from the north, there should be larger and larger circles as you get further away. And we see that for a while, but then after a while, the circles get smaller and smaller again. And we end up with a second pole in the sky. Now, this goes on further. All right. If we go someplace even further south, so I will send us to Chile. All right. Now in Chile, there's a astronomy telescope, the Atacama Cosmology Telescope, which is at 23 degrees south latitude. Now, if we look, what's going on? The southern celestial pole is 23 degrees above the horizon, and northern celestial pole is gone. It's 23 degrees below the horizon. And you can see the lines, that these imaginary lines in the sky are converging toward a point below the horizon. Now, this doesn't make any sense in the flat Earth model, because the flat Earth model would tell you that the reason things appear to set below the horizon is due to a perspective effect. But perspective effects do not make things that are above the ground look like they're below the horizon. The rules of perspective are based on the assumption that light travels in straight lines. And as you get further away from something that's above the horizon, or above the ground basically, it will appear to be closer and closer to the horizon. but it will go more and more, as you get farther away from it, it will go more and more slowly toward the horizon, and it's not until you're infinitely far away that it will actually reach the horizon. Well, the Earth isn't infinitely big, and you can't go infinitely far away from the North Pole. And here in this simulation, we're in Chile, which is not infinitely far away from the North Pole. And the North Celestial Pole is not only at the horizon, it's below the horizon. And if we go even further south, we'll see more of the same. Basically, as we go further south, the South Celestial Pole will get higher in the sky. If we went all the way to the South Pole, the South Celestial Pole would be directly overhead. All right, its distance above the horizon is going to be equal to your latitude, your southern latitude. The angle that stars rise in the east and set in the west is going to be equal to your latitude, or rather the angle between the vertical is going to be equal to your latitude. So here we can see the sun setting at an angle because we're no longer at the equator, we're south of the equator. So what's all this mean? How can you actually test this to see if it's true? So I'm going to go back to New York, because this is a sky I'm familiar with. And in New York, there's Polaris in the north. We'll slow time down a little bit. The stars rotate around, and this is all a prediction. What I've been showing you is stellarium using the globe Earth and the heliocentric model to predict what the sky will look like at any given time and place. And we can actually test this by using the simulation to actually simulate the sky where we are. And in fact, stellarium, when you start it up, automatically shows the sky where you are at the current time. And you can take measurements of the sky. You can actually go out and look at the sky and see that what it's showing you is what is actually happening in the sky. Now, if you click on an object in the sky, so I'm going to click on Polaris here, it will give you a large amount of information about that object. Here's its name, Polaris. These are some different designations it has, some different names that it has in different cultures. We want to look down this list until we get to AZ/ALT. Okay? AZ/ALT stands for Azimuth and Altitude. Now I'm going to set real time so you can see how quickly these things change or don't change. Azimuth and Altitude. Azimuth is basically the compass bearing you need to look at in order to see the object. Okay? So if we're looking directly north, the azimuth is 0. If we're looking east of north, 90 degrees east, and we're looking at the eastern horizon, the azimuth is 90 degrees. If we turn all the way around and we look south, the azimuth is 180 degrees. If we turn further to the west, the azimuth is 270 degrees. And as we turn all the way back to the north, the azimuth is 360 degrees. So now you see I've selected Polaris, and the azimuth here is 359 degrees and 24 minutes. Now there are 60 minutes in a degrees. So this is about 359.5 degrees. So what that's telling us is that Polaris is almost due north, because it's almost 360 degrees away from north. Well, what that means, you've turned all the way around and you're facing north again. The altitude is how far above the horizon the object is in degrees. So here we can see Polaris has an altitude of 40 degrees and 15 minutes. So that's 40¼ degrees. Now, as I mentioned earlier, if you're looking at the North Star, its altitude, or rather the angle between the horizon and it, which is called its altitude, is going to be equal to your latitude, your north latitude. So what we can do is actually go out and measure these things and see if the simulation is accurate. Okay, so, well, there's Polaris. Well, Polaris is not the most interesting thing to look at because it's pretty much always in the same spot in the sky. But if we want to look at something else, so if I click below the horizon, this information goes away. Now we'll look to the east, and we'll see, well, we're looking northeast, we see the star Vega rising. Well, if I click on Vega, here we get a lot of information about Vega. Well, look to Azimuth and Altitude. Azimuth, 54 degrees east of north. Well, okay. Altitude, 18 degrees, 35 minutes. So that's about 18½ degrees. So if we go out and measure the altitude of Vega, we can confirm whether this is an accurate simulation. Similarly, if we go further to the east, well, it looks like there's not a lot there. There's the planet Mars. Okay. Again, it gives you the azimuth and altitude of the planet Mars. Now, what I am suggesting to you is that if you want to test this simulation out, it's actually possible to do this, to measure this altitude using household items. Okay? And what I've done is I went and built basically a homemade sextant out of household items. And I'm going to show you how to do it yourself. Okay, but basically I've got this item right here. This is a protractor. Now, you go out and you get yourself a protractor if you don't have one already, and you want to find one that has a little hole right at the point where the angles meet. And then you're going to put a string through the hole. I just used a piece of thread. And tie it in a loop so that it hangs below the angle measurement portion of the protractor. And then I just hung a paper clip there so that as a weight. And then I taped a drinking straw to the flat part of the protractor so that you can actually look through the protractor or look through the straw at an object, and the hanging string will tell you what angle you're looking at. Okay? So you could make one of these, and then in your simulation, you can see there's the planet Mars at an altitude of now 10 degrees 56 minutes. So that's about 11 degrees. And so you could go out and look at Mars until you can see it through the straw. Put your finger on the string so it doesn't move, and then go look and see what angle, what angle is Mars at above the horizon. Now, the protractor measures, when you're looking straight up, it says 0, and when you're looking horizontally, it says 90. So you're going to get an answer between 0 and 90. And basically what you do is you just subtract what the protractor says from 90, and that gives you the altitude of the object. Okay, and I've done this, and I tried this out. And basically, if you make one of these and you practice with it, you make one and you practice with it, you should be able to get consistently within 1 degree of the right answer, basically. If you point it at the same object once and measure it and do it again and again, you should be getting within 1 degree of the same answer. All right, and if you practice with it until you can do that consistently, then you know that you're actually working correctly. And then go out and look at the sky. Now, I should say, never use this to look at the sun, all right? Because you should never look at the sun directly, because you will permanently damage your eyes. If you want to measure the altitude of the sun, without looking through the straw, point the straw at the sun, and put your hand down near the back of the straw until you can see the shadow of the straw disappear and the sunlight going straight through the straw. Where the shadow would have been, now there's sunlight. Well, at that point, the straw is pointed straight at the sun, and you can take a reading, and see what your altitude is for the sun. And I've tried this out on a number of occasions, and what I get consistently is that the predictions of stellarium, which are, again, the predictions of the globe Earth and the heliocentric model, are consistently accurate. Now, your mileage may vary. I said you wouldn't have to take my word for anything here. So, don't take my word for it. Try this yourself. Go out. Measure the position of Polaris. Does it match your latitude? Measure the positions of bright stars, of the planets. Being careful not to look at it, measure the position of the sun. Does its altitude, as you measure through your homemade sextant, match what the prediction is? Try this again and again. Do it over the course of several hours. Do it on different days and nights. If you can, do it in different places. If you can't do it in different places, use the internet. Contact people who live in different cities from you, who live far away from you, who are willing to do the same experiment. And I think you'll find that when you use this tool, now if you have a better tool, by all means use a better tool. This tool is only accurate to within about a degree. So you'll find that using this tool, your altitude is always going to be within 1 degree of the prediction. If you live in the northern hemisphere, use the internet. Contact someone who lives in the southern hemisphere. See if they really see the stars circling around the southern celestial pole, like Stellarium predicts. Do they? I think you'll find that they do, but really you should do your own experiment. By all means, if you go out and you test this and you're getting results that don't match Stellarium's predictions, make sure you document what you did thoroughly, because if this is wrong, you can prove it's wrong. This is the strength of science. The globe Earth hypothesis is a scientific idea because it's falsifiable. What that means is, if it's wrong, it makes specific predictions. If it's wrong, you can go out and show that it's wrong. The flat Earth is not a scientific idea because it doesn't make these kinds of predictions. There is no flat Earth equivalent of Stellarium for you to download. Why not? Well, the reason why not is because the flat Earth proponents can't agree on some basic things like where the continents are on the Earth and how far away the sun and moon are. And in order to make predictions, you have to basically say, well, this is how far the sun is. This is how far the North Star is. You have to actually be able to say how high they are in the sky in order to make predictions for the flat Earth. The flat Earth does not make these sorts of predictions, so it can't be taken seriously as a scientific hypothesis until someone can actually nail down those figures. And if someone does nail down those figures, then they can make predictions. But if those predictions turn out not to match reality, and not to match reality at least as well as what the globe Earth is saying, then the hypothesis should be discarded because it's simply wrong. But ultimately, it's up to you. Like I said, don't take my word for it. Download Stellarium for yourself. I've put a link in the description to stellarium.org where you can download it. I've shown you how to make a tool that you can use to confirm or disconfirm the predictions Stellarium makes. Go do your own research and let me know what your results are in the comments. Class dismissed.